Dear friends, let us talk about the applications of geophysics in understanding Earth. The Earth is a dynamic planet, perpetually changing both externally and internally. Its surface is constantly being altered by endogenic processes, that is, of internal origin, resulting in volcanism and tectonism, as well as by exogenic processes, that is, of external origin, such as erosion and deposition. These processes have been active throughout geological history. Volcanic explosions like the 1980 eruption of Mount St. Helens in the northwestern United States can transform the surrounding landscape virtually instantaneously. Earthquakes also cause sudden changes in the landscape, sometimes producing faults with displacements of several meters in seconds. Weather-related erosion of surface features occasionally occurs at dramatic rates, especially if rivers overflow or landslides are triggered. The Earth's surface is also being changed constantly by less spectacular geological processes at rates that are extremely slow in human terms. Regions that have been depressed by the loads of past ice sheets are still rebounding vertically at rates of up to several millimeters per year. Tectonic forces cause mountains to rise at similar uplift rates, while the long-term average effects of erosion on a regional scale occur at rates of centimeters per year. On a larger scale, the continents move relative to each other at speeds of up to several centimeters per year for time intervals lasting millions of years. Extremely long times are represented in geological processes, and this is reflected in the derivation of a geological time scale. The Earth's interior is also in motion. The mantle appears hard and solid to seismic waves, but is believed to exhibit a softer plastic behavior over long geological time intervals, flowing or creeping at rates of several centimeters per year. Deeper inside the Earth, the liquid core probably flows at a geologically rapid rate of a few tenths of a millimeter per second. Geologists have long been aware of the Earth's dynamic condition. Several hypotheses have attempted to explain the underlying mechanisms. In the late 19th and early 20th centuries, geological orthodoxy favored the hypothesis of a contracting Earth. That is Paleomagnetism and continental drift. In the late 19th century, geologists discovered that rocks can carry a stable record of the geomagnetic field direction at the time of their formation. From the magnetization direction, it is possible to calculate the position of the magnetic pole at that time. This is called the virtual geomagnetic pole, or VGP for short, position, averaged over a time interval longer than a few tens of thousands of years. The mean VGP position coincides with the geographic pole, as if the axis of the mean geomagnetic dipole field were aligned with the Earth's rotation axis. This correspondence can be proved for the present geomagnetic field, and a fundamental assumption of paleomagnetism called the axial dipole hypothesis is that it has always been valid. The hypothesis can be verified for rocks and sediments up to a few million years old, but its validity has to be assumed for the earlier geological epochs. However, the self-consistency of paleomagnetic data and their compatibility with the continental reconstructions argue that the axial pole hypothesis is also applicable to the Earth's ancient magnetic field. For a particular continent, rocks of different ages give different mean VGP positions. The appearance that the pole has shifted with time is called as apparent polar wander, that is APW. By connecting mean VGP positions of different ages for sites on the same continent, a line is obtained called the apparent polar wander path of the continent. Each continent yields a different APW path, which consequently cannot be the record of movement of the pole. Rather, each APW path represents the movement of the continent relative to the pole. By comparing APW paths, the movements of the continents relative to each other can be reconstructed. The APW path provides strong supporting evidence for continental drift. Paleomagnetism developed as a geological discipline in the 1950s and 1960s. The first results indicating large-scale continental movement were greeted with some skepticism. In 1956, S.K. Runcorn demonstrated that the paleomagnetic data from Permian and Triassic rocks in the North America and Great Britain agreed better if the Atlantic Ocean were closed. That is, as in the Laurasia configuration in 1957, E. Irving showed that Mesozoic paleomagnetic data from the southern continents were more concordant with Du Toit's Gondwana land reconstruction than with the present arrangement of the continents. Since these pioneering studies, numerous paleomagnetic investigations have established APW paths for the different continents. The quality of the paleomagnetic record is good for most geological epochs since the Devonian. The record for older geological periods is less reliable for several reasons. In the early Paleozoic, the data become fewer and the APW paths become less well defined. In addition, the oldest parts of the paleomagnetic record are clouded by the increasing possibility of false directions due to the undetected secondary magnetization. This happens when thermal or tectonic events alter the original magnetization so that its direction no longer corresponds to that at the time of rock formation. Remagnetization can affect rocks of any age, but it is recognized more readily and constitutes a less serious problem in younger rocks. Problems afflicting a Precambrian paleomagnetism are even more serious than in the early Paleozoic APW paths have been derived for the Precambrian, especially for North America, but only in a broad outline. In part, this is because it is difficult to date Precambrian rocks precisely enough to determine the fine details of an APW path. It is often not possible to establish which is the north or south pole. In addition, the range of the time encompassed by the Precambrian, more than 3.5 giga-annum, is about 6 times longer than the 570 million years length of the Phanerozoic, and the probability of remagnetization events is correspondingly higher. In spite of some uncertainties, early Paleozoic paleomagnetism permits reassembly of the supercontinents. Gondwana land and Laurasia are and traces their movements before they collided in the Carboniferous to form Pangaea. Geological and paleomagnetic evidence concur that in the Cambrian period, Gondwana land very likely existed as a supercontinent in essentially the Deutoids configuration. It coexisted in the early Paleozoic with 3 other tectonic centers: Laurentia, North America and Greenland, Baltica, that is Northern Europe, and Siberia. Laurentia and Baltica were separated by Iapetus Ocean, which began to close in the Ordovician, that is about 450 million years ago. Paleomagnetic data indicate that Laurentia and Baltica fused together around late Silurian time to form the supercontinent Laurasia. At that time, the Siberian block remained a separate entity. The Laurentia-Baltica collision is expressed in the tectonic and Caledonian orogenies in North America and Northern Europe. The gap between Gondwana land and Laurasia in the Middle Silurian closed about the time of the Silurian-Devonian boundary, that is about 410 million years ago. Readjustments of the position of the continental blocks in the Devonian produced the Akkadian orogeny. Laurasia separated from the Gondwana land in the late Devonian, but the 2 supercontinents began to collide again in the early Carboniferous, that is about 350 million years ago, causing the Hercynian orogeny. By the late Carboniferous, that is 300 million years ago, Pangaea was almost complete except for Siberia, which was probably appended in the Permian. The general configuration of the Pangaea from the late Carboniferous to the early Jurassic is supported by paleomagnetic results from the Atlantic bordering continents. However, the paleomagnetic data suggest that the purely geometric Bullard fit is only appropriate for the latter part of the Pangaea's existence. The results for earlier times from the individual continents agree better for slightly different reconstructions. This suggests that some internal rearrangement of the component parts of the Pangaea may have occurred. Also, the computer-assisted geometric assembly of the Gondwana land, similar to that proposed by the Deutoid, is not the only possible reconstruction, and although paleomagnetic results confirm that it is probably the optimum one. Other models involve different relative placements of the West Gondwana land, that is South America and Africa, and East Gondwana land, that is Antarctica, Australia and India, and imply that they may have moved relative to each other. The paleomagnetic data do not contradict the alternative models, but are not precise enough to discriminate definitively between them. The consistency of paleomagnetic results leaves little room for doubt that the continents have changed positions relative to each other throughout geological time. This lends justification to the concept of continental drift, but it does not account for the mechanism by which it has taken place. Another aspect of the paleomagnetic record, the history of magnetic field polarity rather than the APW paths, has played a key role in deducing the mechanism. The explanation requires an understanding of the Earth's internal structure, the distribution of seismicity and importance of the ocean basins. Now coming to the second module, that is the Earth structure. Early in the 20th century, it became evident from the study of seismic waves that the interior of the Earth has a radially layered structure, like that of an onion. The boundaries between the layers are marked by abrupt changes in seismic velocity or velocity gradient. Each layer is characterized by a specific set of physical properties determined by the composition, pressure, and temperature in the layer. The four main layers are the crust, mantle, and the outer and inner cores, and summarized briefly here. At depths of a few tens of kilometers under continents and less than 10 kilometers beneath the oceans, seismic velocities increase sharply. This seismic discontinuity, discovered in 1909 by A. Mohorovic, represents the boundary between the crust and mantle. R. D. Oldham noted in 1906 that the travel times of seismic compressional waves that traverse the body of the Earth were greater than expected. The delay was attributed to a fluid outer core. Support for this idea came in 1914 when B. Gutenberg described a shadow zone for seismic waves at epicentral distances greater than about 105 degrees. Just as light waves cast a shadow of an opaque object, seismic waves from an earthquake cast a shadow of the core on the opposite side of the world. Compressional waves can in fact pass through the liquid core. They appear delayed in time at epicentral distances larger than 143 degrees. In 1936, I. Lehman observed the weak arrivals of compressional waves in the gap between 105 degrees and 143 degrees. They are interpreted as evidence for a solid inner core. Lithospheric plates. The radially layered model of the Earth's interior assumes spherical symmetry. This is not valid for the crust and upper mantle. These outer layers of the Earth show important lateral variations. The crust and uppermost mantle down to a depth of about 70 to 100 kilometers under deep ocean basins and 100 to 150 kilometers under continents are rigid, forming a hard outer shell called the lithosphere. Beneath the lithosphere lies the asthenosphere, a layer in which seismic velocities often decrease, suggesting lower rigidity. It is about 150 kilometers thick, although its upper and lower boundaries are not sharply defined. This weaker layer is thought to be partially molten. It may be able to flow over long periods of time like a viscous liquid or plastic solid, in a way that depends on temperature and composition. The asthenosphere plays an important role in plate tectonics because it makes possible the relative motions of the overlying lithospheric plates. The brittle condition of the lithosphere causes it to fracture when strongly stressed. The rupture produces an earthquake, which is the violent release of elastic energy due to sudden displacement on a fault plane. Earthquakes are not distributed evenly over the surface of the globe, but occur predominantly in well-defined narrow seismic zones that are often associated with volcanic activity. These are A. the Circum-Pacific Ring of Fire, B. a sinuous belt running from the Azores through the North Africa and Alpine dinerite Himalayan mountain chains as far as Southeast Asia, and C. the world-circling system of oceanic ridges and rises. The seismic zones subdivide the lithosphere laterally into two tectonic plates. A plate may be as broad as 10,000 kilometers, for example, Pacific plate, or as small as a few thousand kilometers, for example, the Philippines plate. There are 12 major plates, that is Antarctica, Africa, Eurasia, India, Australia, Arabia, Philippines, North America, South America, Pacific, Nazca and Cocos, and several minor plates, for example, Scotia, Caribbean, Juan de Fuca. The position of the boundaries between the North American and South American plates and between North American and Eurasian plates are uncertain. The boundary between the Indian and Australian plates is not sharply defined but may be a broad region of diffuse deformation. A comprehensive model of current plate motions called as the Newell 1, based on magnetic anomaly patterns and first motion directions in earthquakes, shows rates of separation at plate boundaries that range from about 20 millimeters per year in the North Atlantic to about 160 millimeters per year on the East Pacific rise. The model also gives rates of closure ranging from about 10 millimeter per year between Africa and Eurasia to about 80 millimeter per year between Nazca Plate and South America. That is seafloor spreading. One of the principal stumbling blocks of the continental drift was the inability to explain the mechanism by which drift took place. Wegener had invoked forces related to the gravity and the Earth's rotation which were demonstrably much too weak to drive the continents through the resistant basaltic crust. A. Holmes proposed a model in 1944 that closely resembles the accepted plate tectonic model, that is Holmes 1965. He noted that it would be necessary to remove basaltic rocks continuously out of the path generations of a new oceanic crust as a process that was dispersed throughout an ocean basin. At the time of his proposal, the existence of the system of oceanic ridges and rises was not yet known. The important role of oceanic ridges was first recognized by H. Hess in 1962. He suggested that the new oceanic crust is generated from upwelling hot mantle material at the ridges. Convection currents in the upper mantle would rise to the surface at the ridges and then spread out laterally. The continents would ride on the spreading mantle material carried along passively by the convection currents. In 1961, R. Deeds coined the expression seafloor spreading for the ridge process. This results in the generation of lineated marine magnetic anomalies at the ridges, which record the history of geomagnetic polarity reversals. A study of these magnetic effects led to the verification of seafloor spreading. That is plate motions on the surface of a sphere. One of the great mathematicians of the 18th century was Leonhard Euler, that is from 1707 to 1783 of Switzerland. He made numerous fundamental contributions to pure mathematics, including to the complex numbers and spherical trigonometry. A corollary of one of his theorems show that the displacements of a rigid body on the surface of a sphere is equivalent to rotation about an axis that passes through its center. This is applicable to the motion of a lithospheric plate. Any motion restricted to the surface of a sphere takes place along a curved arc that is a segment of either a great circle centered like a circle of longitude at the Earth's center, or a small circle. Small circles are defined relative to a pole of rotational symmetry, such as geographical pole, when we define circles of latitude. A point on the surface of this sphere can be regarded as the endpoint of a radius vector from the center of the Earth to the point. Any position on the spherical surface can be specified by two angles akin to latitude and longitude, or alternatively by direction cosines. As a result of the Euler's theorem, any displacement of a point along a small circle is equivalent to rotating the radius vector about the pole of symmetry, which is called the Euler pole of the rotation. A displacement along a great circle, that is the shortest distance between 2 points on the surface of the sphere, is a rotation about an Euler pole 90 degrees away from the arcuate path. Euler poles were described in the discussion of the conservative plate margins, and they play an important role in paleogeographic reconstructions using apparent poles. Coming to the forces acting on lithospheric plates. Some forces acting on lithospheric plates promote motion while others resist it. Upper mantle convection could fall into either category. The flow of material beneath a plate exerts a mantle drag force, that is FDF, on the base of the plate. If the convective flow is faster than the plate velocities, the plates are dragged along by the flow. But if the opposite is true, the mantle drag opposes the plate motion. Plate velocities are observed to be inversely related to the area of continent on the plate, which suggests that the greater lithospheric thickness results in an additional continental drag force, or FCD, on the plate. The velocity of a plate also depends on the length of its subduction zone, but not on the length of its spreading ridge. This suggests that subduction forces may be more important than spreading forces. This can be evaluated by considering the forces at all three types of plate margin. At spreading ridges, upwelling magma is associated with the constructive margin. It was long supposed that this process pushes the plates away from the ridge. It also elevates the ridges above the oceanic abyss, so that potential energy encourages gravitational sliding towards the trenches. Together, the two effects make up the ridge push force, or FRP. At transform faults, high seismicity is evidence of interactive forces where the plates move past each other. A transform force, that is FTF, can be envisioned as the representing a frictional resistance in the contact zone. Its magnitude may be different at a transform connecting ridge segments where the plates are hot than at a transform between subduction zones where the plates are cold. At subduction zones, the descending slab of lithosphere is colder and denser than the surrounding mantle. This creates a positive mass anomaly referred to as the negative buoyancy, which is accentuated by intraplate phase transitions. If the descending slab remains attached to the surface plate, a slab pull force, that is FSP, ensues that pulls the slab downwards into the mantle. Transferred to the entire plate, it acts as a force towards the subduction zone. However, the subducting plate eventually sinks to the depths where it approaches thermal equilibrium with the surrounding mantle, loses its negative buoyancy, and experiences a slab resistance force, that is FSR, as it tries to penetrate further into the stiffer mantle. Plate collisions result in both driving and resistive forces. The vertical pull on the descending plate may cause the bend in the lower plate to migrate away from the subduction zone effectively, drawing the upper plate toward the trench. The force on the upper plate has also been termed trench suction, that is FSU. The colliding plates also impede each other's motion and gives rise to a collision resistance force, that is FCR. This force consists of separate forces due to the effects of the mountains or trenches in the zone of convergence. At hotspots, the transfer of mantle material to the lithosphere may result in a hotspot force, that is FHS, on the plate. Now let us conclude the entire discussion. It is not practically possible to arrive at every point on Earth in order to understand it. Therefore, the applications of geophysics makes our job easy. During the last 100 years, the researches in geoscience became successful by virtue of geophysics, including structure of earth, plate margins, plate motions, etc. I hope you might have enjoyed the text. Thank you very much.